Anyway, in this GitHub page, you will find the R Markdown file, and the R Markdown file you can download, and then you could go to download it somewhere, and then you could go to the place where you download it, download the whole repository, like I have it here. Oops, a lot of things there. But there's also the RMD file, and you can open that with RStudio, and then you could theoretically go through the code sections and basically run the whole thing, right? So you can start there, and then whenever there's a code section, you can run this, and then go to the next code session and so on, right? And run all these things. And then hopefully this command might also work. This command actually downloads a somewhat larger data package with some real remote sensing images in it. So that's a package that has a size of about 1 gigabyte, and that you can throw away afterwards. But that I use because cron packages can only have a certain size, right? So you're not supposed to send your 1 gigabyte packages to cron and have it distributed there. So I set up my own repository where you can install things. I think it also works with HTTPS if you prefer.
Do it here. If 1 gigabyte, I can do it now, okay? So maybe not a good idea.
Usually you can do it just now, although Tom says not do it, but it typically works, but just goes a little bit slower if multiple people do it at the same time. That is where the bigger examples come from, but I will go through a lot of smaller examples primarily. First, I will say something. So what are data cubes, right? So we looked a little bit at that this morning, and they are essentially rectangular two-way tables or multi-way tables where there's not a structural difference in type, right? So we have, of course, we think of data frames also as tables. The data frames are essentially collections of records, right? Like a data frame table. The way they are stored is that they're collections of columns, right? Because columns are vectors. Vectors can be of different types. So you can have a vector of numeric, you can have a vector of date, you can have a vector of logical, you can have a vector of factor, right? A categorical variable, and essentially you have a collection of these. And we think of them as collection of records. The way they're stored is that they're a column store format. But in essence, it's not a two-way layout table with the same thing along rows and columns. It's a different. There's heterogeneity along the columns, and there's homogeneity along the records, and that is basically why tables or the data frames are thought of as one-dimensional structure. So one-dimensional tables are also one-dimensional data cubes. Of course, the analogy of a cube fails there, but if you think of arrays as being generic, having one or more dimensions, the table is a one-dimensional cube. So typical data cubes is that they have 2 or more dimensions, then it becomes interesting. The cube metaphor is of course 3-dimensional, but we can also have 4 or 5 or 8-dimensional cubes, although you don't often run into them in the wild. Yeah, so it is pretty hard. Actually, you can find 5-dimensional data cubes. You have to really make an effort and go to era 5, weather forecast data, these kind of things to find them. So tables are a special case of data cubes, but are essentially one-dimensional data cubes, and raster layers are also thought of, raster data are also thought of as data cubes because they have rows and columns and then cell values as the attribute. Then is the question sort of what are arrays, what are data cubes, and what are dimensions of data cubes? Yeah, so I was talking about rows and columns of data, but the typical thing for spatiotemporal data cube is that they have spatial properties, and quite often that they might be sort of aligned with some kind of spatial dimension we have, like latitude or longitude, and have some regular, they might be ordered, another property, and they might have a regular discretization, in which case we have a regular raster, right? So it goes on and sort of specializes and specializes. The things I will use library stars that you can, the best is to install it from GitHub here straight away. Then you have sort of the development version. It's also in Chrome. As I mentioned, the vector data cubes, an example is panel data where we have by state and by year, we have a number of socioeconomic data. This is a very common way for aggregated data, for socioeconomic data, for health data, for instance, where you have time series over polygons, comes often this way. If you would plot this, then as I said, this is the tidy layout where everything is in columns and basically stacked. And you see that year cycles fast and state cycles slowest. But it doesn't really matter. If you throw that into packages like ggplot, they really like that, right? They like the tidy layout, and then they can work with that. And you can even plot a raster of these data where you have essentially here, I took the state as the y variable, because then you can still read the labels. I think if you put it along the x-axis, you can no longer read the label, and put year along the x-axis, because we think often as sort of time variability in the x direction going to the right. And you can plot these data this way using color. So we have a two-dimensional table essentially plotted with color intensities as the value for the public capital variable. And what you see here is, of course, it's kind of the most boring thing. It's kind of says, oh, there is only sort of differences between states. Yeah. So this is thing one, and then you start thinking, yeah, well, this is public capital. Let's look at which states. Oh, there is New York, which is very high. Oh, there is California, that is very high. It's very unhelpful that this thing is. Oh yeah, it's ordered from top to from bottom to top. So you can. But then you see, it's kind of the differences between states, which is of course like, okay, yeah, there's more people in those states, so there is also more capital in those states. Yeah, so it's the trivial signal that you find there, and then you're more interested in basically this signal kind of overshouts every other signal. Yeah, so there might be more. What would be the temporal variability? Is there any change over time? You see, for instance, this state goes from a little bit from dark to light, but it's very hard to discern. It's because most of the color range is sort of taken up by the differences in states. So we could do that, and I'm doing that in an array approach where I convert this data set into a stars object with the st_s stars, and this just takes a table. And then it takes the by default, it takes the first two columns to work out the array geometry, right? So it says this is the default of this sts stars method for data frames is to take the two first columns, and then y decreasing is false, meaning it doesn't sort of revert to y ordering, which it would, which would be the usual case for raster data. So I end up with all these variables that start at variable 3, as you see here, region, private capital, and so on, and I move now the first two variables into a dimension table. Yeah, so this is the dimension table where we see that we have 48 states. We have no offset and delta for this thing. A reference system. I will talk about what that means. Nothing known about point, but we have values. Basically, the values for this dimension are the state labels. Right? So the state labels are preserved there. And we have another dimension, which is year, which ranges from 1 to 17, which has an offset and delta, meaning it has a regular discretization, right? So it starts at 1986, and then it has a step size of -1. The -1 is here, sort of, it reverses the order for reasons that you would typically do that by for raster data, which it shouldn't do here. So something went wrong. But anyway, it's fine. But we now have sort of all the things laid out as a 2x2 table. We could, for instance, work on that table by applying things on a certain dimension. So what I wanted to do here is for every row that I see here is take out a mean effect. Yeah, so because these states differ so much in mean, if I want to look at temporal variability, which is my main interest, I would first take out some kind of state effect, and I do that by dividing by the state mean. You could also subtract the state mean, which is another approach. I divide here by state mean and I say, okay, what I want to do is for every state, so I want to apply for something, a function over a dimension of this array, and do that over the first. So I loop over every state and then apply functions, and on the function that takes the vector, that means the time series, and divides it by the mean of the time series. And then I retain the two variable names here. And then I get this thing out that just reverses the order of the variables, but still has the same dimensions. And you can see it's now entirely different values, or the values have been normalized by their mean, by their state mean value. And if you plot that data set and also change the order of X and Y and fill it with a public capital, then you see suddenly that all of the states have the same kind of mean level, mean color level, and that we see that certain states sort of go down and certain other states go up. Yeah? So suddenly we see where we first saw only sort of the main effect of difference between states, which is essentially the size of the state. We now see that the temporal development by state is also varies pretty much. Yeah? So it's an entirely different method. So this is something you can do by saying, I want to do something for all the time series, right? So for all the time series, I apply function. This is functional programming, and do that over a certain dimension. And that is something you can do with apply. Apply works on arrays, and STApply works on stars arrays. And stars arrays are just arrays with a little bit more semantics. Yeah. For instance, it has semantics that we have a regular time series here, although it doesn't know that these are years. It doesn't know sort of how the time information is there. Yes.
May I interrupt? Do you mind?
Yeah, always.
So in this plot, the states are different size. And if you would like to plot that also, that you can see the proportional size of the state, would that be possible?
Well, you see the proportion of the size of the states in this plot by the variable capital. Yeah, so this is the size of the state expressed of the public capital of the state. So of course there are states where people are richer and people are poorer. That's not in here. This is just the amount of something, right? The bigger states, this is the size of the state expressed in this variable. Do that. Yeah. But here, state is just labels, right? So we just are interested in the differences between the states. All right, and I was here. Right, so this is spatiotemporal. It's just that neither time. So we see now that we drop the year numbers. So neither time nor space is referenced, right? So time was just numbers, and we need to know that these numbers refer to years here, and space is state names, right? So we just labels for space, right? And R can deal with those kind of things very well, but the thing is that at some stage we want to make plots, and then we need to associate these. If we want to make plots of maps, then we need to associate these labels of the state with the geometries, with the polygons of these states, and then do that, and then we get real spatiotemporal arrays, right? So we can do that, and we'll do that with an example of the North Carolina STITS data set. So that's a very classic data set that comes back in a lot of examples, and has a long sort of vignette in the SPDEP package here, and that contains data, epidemiological data. It has several called birth, the number of births, then the number of sudden infant deaths. So this is the disease cases, and then another variable, the non-white births, because there was the hypothesis that the disease might happen more or less with white or non-white persons, and was collected for 2 years. And so we have essentially counties, right? For North Carolina, we have 100 counties, and we have 3 variables, and we have 2 years. Yeah, so that is like a table with a 3-way layout: county, the variable, and the time, the year. Right? So we can do that. Here is the table. If you download them and plot them as a table, I used read underscore SF here, so that you get automatically get the thing printed as a table, which some people find convenient, which I find convenient actually. And now I'm going to make this into a matrix. So this is pure base R. So I'm gonna select the variables here that I'm interested in, the 6 variables. because you can see that these variables are spread out over columns. Yeah, so we have the birth, sudden infant deaths, and non-white births for 74, and the year is glued to the variable name. This is not uncommon. We have things repeated in time, and they're essentially different columns in the table because they were associated to the same features. Yeah, so this is, in that sense, it's non-tidy because it's something is distributed, kind of hidden in the column name. Yeah, but that is also not very uncommon. And so we take these 6 variables, and then we're going to convert it into a matrix. So that will be a matrix with 6 columns and with 100 counties, right? But then we're going to change that in 100 by 6 into 100 by 3 by 3, just by setting the dimension of this matrix. And now this works because the ordering of the values in the matrix doesn't have to change. So you need to know a little bit about how this works. And what I also do is that I set the dim names. So that means that for each of the values of a dimension, I give labels. So I give the county labels to the variable county, which is the first dimension. I give this birth, sudden infant death, non-white birth to the second dimension, and I give the year, as you can see here, 1974, 1997, to the third dimension. So then I have a 3-dimensional array, 100 by 3 by 2 array, and then I'm going to convert that into a stars object, and I get this, right? And then it sorts this out, and it says, okay, I have a county dimension, where here the county names. I have this variable which says, is this about births, sudden infant deaths, non-white births? You could argue this should not be a dimension, but I just threw it into a dimension because they're population numbers. And I have 2 years, right? And I have one variable called population. So I have 100 with 3 by 2. So there's nothing spatial temporally on this. It's just a regular R array with labels. Yeah, and the labels end up in the dimension values if I convert it into a stars object. Yeah, so it's the way sort of the dimension names end up is here. But there's still nothing about reference systems. There's nothing about geometries. There's nothing about knowledge that years is actually a time variable. Yeah, that will all come a little bit later. What I know now is that from sort of a data cube with labels, with labeled dimensions, I'm going to convert this into a spatial data cube by setting the geometry of the North Carolina counties to the values of the first dimension. Yeah? So I have this stars object here, which I had here, and I have here the values, which are the county labels, and I'm now replacing that with the actual geometries. Yeah? So you see now that the values are no longer county labels, they're gone, but they are geometries, right? They're abbreviated simple feature, multi-polygon representations of yeah. So the geometries are actually in there now. So now I have an object that is spatiotemporal. And what you also see is this little thing is that there's a reference system now, which is the coordinate reference system of the coordinates. Yeah. So these coordinates only make sense if you know what they mean, right? As these degrees, latitude, longitude. If yes, to which datum are they associated? They are the datum associated to the North American datum from 1927, or are they projected, and what is the sort of the description of this projection? That all goes into this reference string, which is for spatial data, which is the coordinate reference system. Yeah, so it has spatial data now, and it has a spatial coordinate reference system that ends up here. So this is something that standard R arrays cannot do. You cannot sort of go further than just add dimension labels. Yeah, so textuals, it's like a little bit like what I think NumPy or so also have labeled dimension or X-array and so. But if things are spatial, then you need to put a little bit more information in there to make this understood and interoperable. And these are kind of ugly things, right? They are polygons, multi-polygons, holes, and everything. So the whole sort of the whole terrible thing that essentially is solved by the SF package is in there. You don't have to worry about it. So what could I do now? Well, I would like to plot them. What shall I plot? I have to think. There are 100 counties, so I could make 6 maps out of that. What I did is make 3 maps, but take the sum of the years. Yeah. So I say I'm going to loop over the first 2 dimensions. So I'm going to loop over the counties and over the variables. and then take the sums of the third. Yeah, here's the sum, here's the function that I call as a third argument, apply sum to the third. So I mean that I'm summing all the 1974 and 1979 cases, and I get then up. That means that I reduce this dimension, yeah, so that I end up with a 2 by 3, yeah, so a 2 by 3 layout. And if I plot that, the counties are plotted for each of the 3 variables. Yeah, whether this makes sense or not, but it's an exploratory plot, and you can still see some colors, which is convenient. You see some variability, although these disease cases are extremely low. They're pretty close to 0. And the births are, it's kind of one thing that happens in 1 in 100,000 cases, but you still see some variability because the default plotting scale, the color range, is cut into quantiles. Yeah, so it takes essentially the whole cube, all 3 maps, and then looks at whatever it takes, like 11 different colors, and takes the quantile values. So you still see a bit of variability in the lowest map as well as in the highest map. Although the values you cannot read sort of what the true color breaks are here. Yeah, you would have to compute that a little bit, or choose a log scale or something else. You could do all kinds of things there. So if you want to analyze these data meaningfully, then there's again this problem that we have states with more disease cases and sort of counties with more disease cases and counties with less, but then also there are counties with more people and counties with less people. So these are just the counts, right? So we anyway looking, when we look at the disease cases, we are looking at a population distribution. So you want to take that out. So you want to sort of have the relative numbers. So where are sort of relative to the amount of births that happen, where are the sort of the more sudden infant death cases, and relate to that. And the usual way, or one usual way to do that, is to go from raw counts to standardized incidence rates, SER values, by computing the incidence over the population and dividing that by the mean of that ratio. Yeah, so the mean incidence over the total population for the whole region. Yeah. So this is a job that we basically can do over that we have to do over these 3 variables. So we have to do that for every year, and then basically relate the SID cases to the birth cases. SID is the CIs and birth is the PIs, right? And that is what I did here. So what I'm going to do now is to move to split a dimension over an attribute. Yeah. So like a data frame, we can have several variables. In this case, we have one array, 100 by 3 by 2 array, which is population, and it's a mix of birth counts and of disease counts, right? But if we want to sort of do the ratio of the disease over the births, we can as well split that over attributes, and that means that we now not have one population variable, but we have 3 variables. These 3 arrays are now 100 by 2 each of them. So 100 counties have each of them have 2 years. Yeah, so that's another raw way of looking at the data. There's not a correct way. There is just whatever is convenient, and you can split and you can merge, so you can sort of lay out a dimension over different variables as you would when you create a data frame. This is a list of arrays, so it is kind of a data frame that is smart enough to understand dimensions. You can split them and you can merge them again. So we splitted them here. And what I did then is, over this splitted data frame, I computed the sum, yeah, just over this list. Yeah, so this data structure is just a list, so I can do an sapply, which is a base R function that just looks over a list and sees what's there. And for each element of the list, I compute the sum, so I get the totals, the total births, total SIDs. Yeah, this is the total births, total SID. So that gives me the denominator here, the totals, sum of CI and sum of P. Yeah, so I have the sum of births, sum of SIDs, total, whole data set, and I can compute that ratio, right? So that gives me the normalizing constant, so to speak. And then I'm going to use that to compute for every county and every year. Yeah. Now I want to do this for every county and every year. So I'm going to apply to every county and every year. I'm going to compute the ratio of CI and PI. Yes, for every, so this function is an anonymous function. It just gets a length 3 array, right, with the birth, the sit, and the non-white birth values, and I just want the ci and pi, so the sit value over the birth value. So I'm going to just compute that ratio and divide it by my normalizing constant, which was the mean ci over pi for the whole data set, and that gives me the standardized incidence ratio for this data set. Yeah, so it's a few lines of code, and it looks very complicated, but you just do things. You do it now for every county. Now do things for these variables. Now do things for every year, and so on. So it keeps track of that. If you just you know, as an exercise, do the same thing for a regular table. You can also do that. Yeah, it's not rocket science. It is just, in my eyes, it's much more complicated to do it the other way around. And the advantage here is that we end up with two maps. Yeah, we just don't end up with a table that we then again have to link to geometries, but we end up with two maps because the geometries are retained and the years are retained. And I have zero values for the 2 years. And those are then can then be compared. So these two maps are then typically the input for further analysis and do questions like, okay, is there a difference between the 2 years? Is there some kind of a regional effect? Are there regions that are higher or regions that are lower? Is there some kind of clustering in this pattern? And is there, yeah? So this is typically the input for spatial statistical and epidemiological modeling with some kind of lattice data models. You see here that I took a dedicated color scale. So I took a dedicated palette, which is a diverging palette, which goes 2 colors from the center. And I took dedicated color breaks here because the value 1 is special, because the value 1 says that I'm identical to the mean. Yeah, so white cells are pretty much identical to the mean. Red cells means that I have incidence values that are higher than the average over all the countries and over the 2 years. And blue cells means that there are cells that are lower. Yeah? So the value 1 is kind of identical to the global incidence ratio. Yeah? That's a normalizing constant. So this is much more informative than focusing on maps like this, which are the raw counts, which contain, yeah, the SIP map contains the signal of the birth count. So it's impossible to see whether there's higher incidence rates. And as I said, the advantage of doing it this way is that you can work on dimensions directly, and you end up with maps where the spatial data is still retained. Yeah, so are there any questions related to that? And so, yeah.
Geom stars, you have Geom stars for digital too. That doesn't seem to work for this data set. What do you mean?
Oh, that should actually work for this. Oh, good question. Yeah, I think it should work. Well, let me just, yeah, I think it should work because it splits, Geom stars sort of looks at my raster data and my vector data and then calls Geom SF in case of vector data. So it should, but let me sort of, you're catching me off guard, obviously. Yeah, there's always a lot of things that don't work, that might work. Yeah, but yeah. Right, and then you can go on and you can call a map view. Map view, as the current situation, has a little problem that it didn't work with Markdown very well, so I outcommented that. But you could look at these plots interactively on a leaflet background and see where these things are or what the state of the names is if you click on a particular county. Okay, let's take a second dive into vector data cubes. So vector data cubes are very convenient for cases where you have not just sort of vector data with attributes, but kind of structure in the attributes in the sense of you might have a time series or you might have a set of variables that is in some way related and you want to work with that on that as a dimension. Let's look at a more complicated or more challenging case where we have more than one space dimension, and the case there is the case that I worked out here is that of origin destination matrices. And that case has been worked out here in 432 of a book that is very slowly progressing, that builds on a data set that Robin Lovelace, one of the authors of the geocomputation with our book, shared. And that is an origin destination cube from the Bristol region. It's going to. And the thing there is that origin destination matrix basically are numbers about relationships, right? So we have here, let's say we have 100 counties or 100 districts, and we have origin destination data. So that means we have, for each district, we have the number of people moving to another district. Yeah, this is sort of people live somewhere and commute to some other place and use a particular transportation means. And we have, for every transportation means, we have the number from every county to every other county. Yeah, so we have sort of a matrix, right? A table layout of the origin regions and the destinations, and then the numbers are numbers of people. And then we have, of this table, we have several. We have the numbers where people take the bike, the numbers where people take the train, where they take the bus, or where they go by foot. Yeah, so that is a two-way layout, a three-way array, right? Where two of the dimensions are spatial, yeah, are spatial vector. They are the districts. And here we see the district and district of one zone lighted up here with zone 33, because we will focus a little bit on that. And if you look at the original data, the OD data, it has the origins, it's a table. It has the origins, the destinations, it has all moving people, and then sort of split up by travel mode, right? So we have essentially the sum of these four variables here, and then we have them split up. So we have, but they're all moving people, they're just in different modes, right? So we have, you could argue this is not tidy because it's all moving people, and we can't sort of make this dependent on mode because mode is sort of distributed over columns. Yeah, so this is one way you could organize these data. And of course, the advantage is that you only have the combinations of, you don't list, probably this table doesn't list all the zero entries, because there might be a lot of zeros, but lists all the positive entries. But as you can guess now, we're going to reorganize that, and so we're going to do some gathering. So we do this with tidyverse, and here is the gather and spread. Gather and spread are they're now called pivot wider and pivot longer. What gather does is basically that it gathers a couple of variables and sets them, sort of stacks them. Yeah, so it sets the foot and then the car. So we get one variable, and then it repeats all the other things, the destinations and origins. So we get an OD with the mode, yeah, the bicycle, and the number. Yeah, so I now drop this all variable, but I'm going to stack all these four variables into one thing. And then I need to make a couple of manipulations to make sure that I fill a matrix or an array in the right way. I'm not going to go in all the details of that, but what I end up then with a little bit of magic. Basically, I have to do some matching here because the table is not full. It just might contain. It might have dropped all the zero entries. I'm going to make this into sort of a full array that has two spatial dimensions here, origin and destination, O and D, and it has a mode. And we see that the spatial dimensions are multi-polygons. They're identical, of course, and they are geographic coordinates related to the WGS84 datum, and otherwise they don't have any information. But what you have is the values, is the mode essentially, which is the label of the fourth dimension, which is the travel mode. And then I can do all kinds of manipulations that are of interest here. This is the full table. You see that there's a lot of zeros now, but there are no NA values because, of course, the NAs would be filled with this is contingency, this is frequencies. The NAs would be filled by zero. And I can plot, for instance, here. And what I did is do a subset. And I sort of subset means The first comma means that I'm going to use all attributes. The second means that I'm going to use all the values from the first dimension. And the third means I'm going to use the 33rd of the second dimension. The second dimension is destination. So I'm going now to do a slice of this three-dimensional cube. I'm going to slice through the destination dimension and take destination 33, right? So I get now 4 maps, the bicycle, foot, driver, and train maps for all the people that move with to destination 33. And that's the highest, the destination with the highest sort of, it's the city center, right? So this looks at all the people going to destination 33, where they come from, how many, and what is their mode. What is their transportation mode, right? That's in these 4 maps. And you can just do that by say, give me this plot with destination 33. Yeah? So I slice this two-dimensional data, do a slice over one of the spatial dimensions. So the other one I can map, right? You cannot sort of do the map of all the combinations. That would be a lot of maps. Now I can also sum, for instance, this thing over the second dimension, so over the destination, and then look at which district is my maximum. That is this 33. Yeah, that's the reason why I picked 33. It's the city center, and also look at, for instance, the sums of the 4 transportation modes. Right, sum over the 4 transportation mode and get this array where the 4th dimension is gone. I can also do the origins, the origin totals by mode. Here you see the origin totals where I essentially summed over the 1st and the 3rd dimension, and a destination totals by mode by summing over the 2nd and the 3rd dimension. So you get a lot of summary statistics, essentially by very simple code by taking these origins or destinations as a dimension on the cube. Right, so here I took these sums and over the origins and the destination, and I plotted them side by side using a log scale for the variable. So you see some kind of reasonable variability expressed. Here you see the destinations. Here you see that the origins are much more spread and the destinations are much less spread. And you can do some kind of further computations on these kind of things. Yeah, so this is an example where you have a more complicated data set. And again, you can do all these manipulations by manipulating the tables, using tidy, using dplyr type of things. But it's a pretty high likelihood that it will be very clumsy and look much more complicated to do it that way. So that was a more complicated example with two spatial dimensions, 2 fully spatial dimensions, right? So both the origin and the destinations are 2-dimensional spatial, are about polygons. Yeah? So these are vector data cubes, and before I go to raster data cubes, I want to sort of wrap up that vector data cubes basically could be stored as data frames or tables. The thing is that when you work with arrays, it is immediately clear where you have your missing values or where you have your 0 frequencies, if these are count data. So the table that Robin provided, it's not immediately clear that there are not duplicate records in it, and it's not immediately clear where the records with 0 frequencies are, because it's basically it just stores the positive numbers. Yeah, that is the information you have. So that is that's information that's convenient to fill that, basically to complete that, to fill that up. Duplicate records is a potentially a problem. Also, if you work with the same data in tabular form, then there is no index to data, right? So the order of the records is not given, and probably you're going to do a particular kind of analysis where the order of the records doesn't matter. That means there are no indexes. Anyone familiar with anyone who ever worked with really sort of larger data sets where you have to wait for an hour or days or something like that on computations, and it's about databases and finding data, then everyone would know that having indexes in your data is the thing to speed computations up. Yeah? Indexes mean that you know in advance, or you pre-compute where a particular record is. Yeah? And if your data are in an arbitrary order in a very large table, then you need to go through it and go through it and go through it. Right? This is one of the reasons why data.table, the package, is so much faster, because precomputes and stores indexes on variables. Yeah, it does basically what a database also can do, and that our data frames do not do. And if you have large data, that makes a lot of sense. Arrays are just there. The only reason they are there is that they are the indexing. Yeah? If you know that sort of, if you want to know sort of the combination of the 22nd origin and then the 54th destination and then the travel mode foot, then you know in advance exactly where to look up that value. That's the way arrays work. They're not just tables. They are clever structures that where you have pre-computed where everything is. You have that in it. You have it. So it's a very fast way of getting to the data that you want. And the other thing is that you can directly operate over dimensions. You don't have to sort of go through all the records. No, you just directly operate on the dimensions. Say I want to sort of have the ratio of the disease cases over the total population, and that is just two labels or something like that, right? And also, vector data cubes arise naturally when you sample raster data cubes. Yeah, right? The raster data cubes are up next. Quite often, you want to sort of look at what happens in this raster data cube at these set of sites, or what's going on for these. How do I summarize these raster data for this set of polygons, because somebody wants to know this at a polygon level because it needs to be connected to socioeconomic data or something like that, reported. And so vector data cubes arise naturally when you do sampling or aggregation of raster data cubes to points or to polygons or even to lines. Why would you not do it? Well, tables may be more efficient. So the data cubes that I look now at are all dense data cubes where I store all the combinations. Right? A more clever way would be in the origin destination case that it would only store the non-zero values, right? And that would be a sparse array, which I didn't look at. And you can do sparse arrays, but it's just more specialized, right? We often don't do that. Things on disk are quite often anyway compressed. Another reason not to do it is rather than be smart, use raw power. Yeah, so there is a trade-off between sort of the amount of time you're going to put into developing a dedicated analysis that's very fast. Yeah, so the analysis would get faster and faster, but the time you spend on getting this done gets more and more. And so the total cost of your study is the combination of the time you need to wait for the result and the time you had to develop the solution. Yeah, so when I talk about raw power, then you can say, well, I know how to do this with tables. I just, I'm going to throw it at some infrastructure that is going to do this for these big tables. It's going to work. Yeah, so this is essentially the sort of the higher idea behind Google BigQuery GIS, which is a post-GIS on steroids. Yeah, so you could throw terabytes and petabytes of data against it. Yeah, at very small compute costs, and get your thing done on a tabular format. It's just table. It's just so it's a way to work. This is also how the company Carto essentially does everything with vector data. Yeah, they're doing everything with vector data. Look at their logs and so on. They're doing raster analysis with vector representations of their data. They just, either they points or small polygons, whatever, doesn't care. Just because it's easier to do everything in the vector context, and it doesn't matter. When it is there, it's there, right? So you get things done. So I wouldn't say that this is the future, but it is definitely something that might be, in certain cases, the cheaper option. Okay, then we move on to, so any questions about vector data cubes or my remarks about big computation and so on? Yeah, so there's not a truth. There is different paths lead to hopefully to identical results. Yeah, they should. Okay, then I'll move on. Yes.
The hexagons and global grid with equal area.
Yeah, global grid. Discrete global grids are an interesting topic. And I'm not really going to.
There's a person who made a package, but he's only going to present tomorrow.
Richard Barnes developed a package called DG Grid, Discrete Global Grids, for hexagon grids covering the Earth. Together with Dewey Dunnington, I did a lot of work the last couple of months on a package called S2, which has a different discrete global grid, the S2 grid that powers all the Google infrastructure, which is based on a cube representation and sort of quad trees on cube sites. and these are essential indexes on spheres. Yeah? So when I talk about array indexes, the typical raster thing that I will now go into is like is a two-dimensional. The idea is that you have two-dimensional space and have an image with rows and columns, and that is fast. And that is fast, but if you have global data, then the flat representation is typically not so useful. Yeah, you could do a longitude latitude grid of a certain grid size, but then your cell sizes at the pole are very small and they all touch each other, so you get these problems. Yeah? So discrete global grids are efficient ways of cutting up the Earth, the sphere, into similarly sized parts that can be hexagonal, that can be H3 and so on.
And they're nested, right?
And they can be nested, or they could be semi-square, like the S2.
Many people tell me we should all use hexagons.
Yeah, it depends. It depends on the problem. So if you have global data, it's not a bad idea, but it really depends, I think, on how important it is that your cells are reasonably equally sized. If you do computations anyway, and sort of, if you're able to compute the size of your cells and take that into account, then you're also fine, right? Then your cells are just unequally. So it's not like forbidden to do longitude latitude grids. Well, it's a stupid thing. It's just very inconvenient if you're at a pole. If your region covers the pole, it's extremely inconvenient. So then people sort of do that, and they turn the Earth so that the equator goes over the pole, and that kind of tricks. Yeah, so that's a somewhat, it's a very interesting discussion and relevant, and it's a way. So there are very clever ways of indexing spheres, indexing the globe that are good, and hexagons is one of them. You could do it this way, and you just have a list of hexagons and put that in an SF structure, and that would work with stars. It's just that stars doesn't know about the indexing very well, right? It just says, oh, this is just a very large collection of hexagonal polygons. Whatever I'm going to do with that. Yeah, but then if it would do geometrical operations on it, it uses S2, which is again blazingly fast, right? But has a different indexing structure. So raster data cubes.
One more question here.
Yeah, sorry.
Please, can you repeat the question, because of people online, people complain that they don't hear the question.
Okay.
The back also.
Okay, we'll repeat the question for the back and for the onlines. Yes.
So stars is an abbreviation for spatiotemporal array, I think, right?
Arrays.
Arrays.
Yes.
But it's not necessarily spatial. You can take it, like you showed in the beginning, be something that's totally non-spatial. Right?
True. Yes.
It just needs to be multi-dimensional.
Yeah. It's so repeat. The question was stars. What does it stand for? Spatiotemporal arrays. But the examples I started with are essentially non-spatial, non-temporal arrays. They're just generic array data, and that is covered as well. It is just that it doesn't have that many benefits in that case. Yeah, if I just have labeled arrays, I could work with raw R arrays and do everything with apply on them. Yeah, so then also the dimension labels are being kept. Apply sort of propagates the dimension labels. So R has a rich sort of infrastructure for dealing and handling, subsetting, slicing, analyzing, aggregating, reducing arrays, permuting them, combining them, and so in the package A-bind that stars also uses. Yeah, but there, and on the non-spatial, non-temporal things, stars adds very little. Yeah, there's little benefit in using it. It just sort of passes it on to what R already does. Okay. So raster data. So here is a test.grd file that I read from the raster package, and I read it with the command read_stars. So read_stars tries to read raster data using GDAL, and this is a vector format that actually is dedicated for our raster data sets that GDAL can read, and that we get here. So we get the sort of the test.grd variable, and you see that I get two dimensions here, x and y. So I now have two spatial dimensions, yeah, two dimensions, x and y, that kind of together sort of describe space. Yeah, so this is an extremely different situation. I have X and Y, and I need both of them to sort of find a certain location. So in vector data cubes, I had just a sequence of either points or polygons or lines, whatever, that each of them describe 2 or 3 dimensional space. Here I need 2 dimensions to essentially to get that. Yeah, I could select a value sort of for X and take X with value 3, and then I would get a constant X, meaning I would get a column of my raster out of this. Yeah, I could select a column, or I could get a column subsection of that raster by selecting X values. So we see here that several things. We see that X ranges from 1 to 80, so it's an 80 by 115 array, but that we also have offset and delta values. And offset means that is where the raster starts on the X side. So the X edge of the raster is the offset, and the Y edge is the Y offset. And since Y values, Y delta, so delta specifies the step size, so the grid cell size in X and the Y dimension. And you see negative Y values, negative cell sizes in the Y dimension, for the reason that the Y coordinate increases when the row index goes down. Yeah, so they have an opposite direction. So that means a negative cell size. Y goes up, going north, but typical images have cells that the image, when you plot the image, it goes from top to bottom, right? This is the way image data is almost always stored. You don't have to do that. It can also be the other way around, but almost everything that is stored on file is stored that way, because PNG, JPEG, everything does that, right? Images start bottom to top. So that is the delta, and we have a reference system, which you can see here is these Perch4 string, which are now deprecated, and the other things are missing. And we have a special label that says here, is this one of the X and Y? Yes, this is the X and this is the Y. The reason is that not always X and Y are called X and Y. They might be called latitude and longitude, or lat and long, and so on. And somehow they need to be mapped to what is going to be plotted as the X and what's going to be plotted as the Y. This sounds trivial, and it's not always trivial. Yes, there are a lot of cases where, you know, if you have a polar projection, it's not clear what is northing, right? So these kind of things. And then if you plot it, we use this theory, this scale, and we use equal breaks, and we get the usual plot of this Muse data set. So we see here a couple of things. Raster files are data cubes. The attribute has the values for all combinations. So also the white cells here are filled with NA values. Yeah, you see here that I have 6,000 NA values. So this is all, sort of the whole raster is filled, and I just show the colors for the non-NA values. Where vector data cubes have a single spatial dimensions, raster data cubes have 2 spatial dimensions called X with X and Y labels, or they might have 3 if it's a 3-dimensional data cube with voxels or some kind of meteorological data and so on. This case is an example of a regular grid. That means that offset and delta are filled, and that indicates that we have constant cell sizes in each of the directions. Yeah, here there are also square cells, but as you see, they don't have to be square cells. This one might be 40, this one might be minus 50. Yeah, it's fine. Yeah, but they're constant over the space. That means that I can compute my coordinates from the index by this equation. Yes, if I have offset and delta, and I want to know the coordinate of index index I, then I can compute it this way when my index is 1 based, and then for the value 1, I get the cell edge, and for the value 1.5, I get the cell center. Yeah, so we have the cell space essentially, which is continuous, and the index, which is also then thought of as continuous. Yeah, so this took a while before I understood, and then Y is the delta for Y is negative. That means that the coordinate values decrease when my index increases. Yeah, when I'm going down. Also, the dimensions have a reference system. That means that I can link this data to other spatial data and put it on some place in the Earth. What is plotted are the non-missing valued cells. What I can do is with this data is convert them into an SF object. Yeah, that means make them vector data. And what then happens is that, and then I say, don't remove the missing values, which would by default happen. Just to show you, I get polygons, so I get here then 9,200, which will be the product of 80 and 115 polygons. And if I plot these, then I get a plot like this. So you see the little polygons plotted, where I also plotted the polygon borders in gray. So you see now all the grid cells plotted as small polygons with a gray border, and the values filled whenever there are non-NA values. Yeah, so you get the same map in a vector representation. Yeah, so you can equally do that. Yeah, this is what I meant by what Carto does and what BigQuery GIS would do. Just look at the whole thing as a bunch of polygon data. And it works also. But of course, you wouldn't do this with massive grids, right? This works nicely because it's a relatively small grid. Yeah. So if you're going to do this with very large grids, then you're going to set your computer on fire, right? Not literally, but sort of it will sort of require so much memory that your processes break down and things like that. These things actually become really interesting when I use raster, when I use multiple layers, raster data cubes, so-called raster stacks. Yes, you have a question.
Just a brief question to something before.
Yeah.
You said xi, we calculate the xi with the offset, right?
Here.
Okay, so that's the left edge.
Yeah.
And for y, is it the top or the bottom of it?
There is a value offset and delta that you find in this table, offset, delta, and you fill that in this equation, and you give it an index.
Sure. I know about that, but
yeah.
I'm asking, so that's the left edge of a box, say, yeah? Or some
yeah.
area, okay. So, and the y, is it the top reference of the box?
The question, I'll repeat the question. Yes, I said, for X, I can see how this works. It's the left side. Yeah. For Y, is this the top or the bottom? Yeah. And here is the magic. It depends on delta, right? Delta is either positive. If delta is positive, then an increase in index means you get an increase in Y, you go up. And the offset will be the bottom edge. If the delta is negative, taking an index of 1, the first thing, cancels this element, means that the offset is the top edge. Yeah, so the meaning of offset depends on the sign of delta. Yeah, that is the trick, how to think of offset and delta. Yeah, thank you. Good question. Right, multiple layers. So here's an example from the ArcGDAL package, which has a familiar JPEG image. You can also read JPEG images. And reading JPEG images is not a problem. You get 3 bands, RGB bands, because it's a JPEG. And you see that here are dimensions, and you see that these are regularly discretized. I again get an offset which is 175, and there's a delta of -1. So again, it's going down, indexing. But the reference system is missing. Yeah, so it's regular, but this is not Earth data. This is just an image. Yeah, and that is also why the cell size is 1. But GDAL can read such nevertheless. Yeah, but it's just unspatially referenced. And you get the intensities, yeah, in values from 0 to 255, which is typical for such images for JPEGs for the 3 bands R, G, and B. And then it can use the function st_RGB that computes RGB values. Yeah, so R has values for colors. So you can use the RGB function to compute a. It needs to be. Max color is 255. It gives you labels. Yeah, this is text data. This is character data. It gives a hex representation of a color that can also include an alpha value. And this basically throws these 3 bands together, or possibly an alpha band as well, and sort of converts that into color values. So that reduces the 3rd dimension, the band, and I get these color values out. And when I plot that, you see the sort of regular RGB thing. I don't know why it's not plotted. You know, it's the it's the thing you've seen before. Let me try. Here it was. So I need to. Yeah, I'm, you know, I'm not so good with I'm not so good with RStudio, to be honest. It's very embarrassing. It's very embarrassing. Ah, yeah, this is it. Yeah, thank you. Yeah, thanks. And then you get the unsurprising, you get the color map of the R logo. Then it puts RGB on top on, computes the colors. Right, so this is something you can do to compute colors from values. Right, multi-band data is more common when you handle satellite imagery. Here's an example of an excerpt of a small Landsat 7 image used for, that covers part of Brazil. You see it has 6 bands. It has all the 30-meter bands, and they are in UTM zone 25. Yeah, so Landsat data is in UTM. You also see here that the point label is set to false and no longer to NA. That means that the data set that we have been reading here, that this TIFF file, has metadata that tells you that pixels are actually, the pixel values are associated with spatial areas and are not associated to point values. Yeah, there's a difference between one and the other. You could have other data sets like DEM data, digital elevation model data, where your pixel values refer to an elevation at the cell center. Yeah, that has a different semantics. If you then would sort of zoom in, you would like to interpolate values rather than draw them as square boxes. Yes, here interpolation is sort of harder to imagine. Of course, this doesn't mean that these cell values are a constant value throughout the cell. They're just associated to the square, and they're, of course, they are convolutions, because this is an image sensor that sort of measures averages over small areas that are not even square. Right, and if I plot that, then you get a plot like this, and it essentially histogram stretches over these 7 bands, right? So it takes all the values of these array. So this is a 350 by 350 by 6 array, takes all the values and then takes the quantiles and sort of assigns colors. That means that for these 6 maps, the 10 different gray scales are kind of equally distributed. Yeah, so it's similar to what you do with high dynamic range photography, that you kind of distribute colors equally, not get very large light or dark areas. Yeah, that you see something. If you would do it in a standard constant or equal interval range, the way that raster does it, and in most of the times all the maps will have the same value and will be all dark or light. You don't see anything. Yeah, so that you can override it. Here I did the same thing, but then I didn't do this with a joint Z limit. So here all the maps sort of revert to a single color scale, but I can also do the histogram stretching for each of the bands. Yeah, so I do that here. So here you see even more color stretching, and of course no key anymore, because each subplot now has its own key. Yeah, has its own color breaks. Yeah, so you can do this to sort of blow up variability. And it also maximizes space in your plotting region so that you see something, right? Instead of putting legends everywhere. Right, so you can then also do RGB composites. Here, this is the true color composite. This is some kind of false color composite by computing by computing RGBs. This is by plot and using the argument RGB. I could also do strGB with a band selection and then compute the RGB values and plot them. It's different ways of doing this. Transforming and warping rasters. There is the thing that if I want to sort of combine Sentinel-2 and Landsat 8, then it might be the case that these two don't have the same coordinate reference system. This is definitely the case if you put something on top of MODIS data, which is this sinusoidal grids, then you need to work with that. You need to do something. And this, to illustrate that, I created a little data set here with this bounding box. Yeah, this is pretty much sort of a large section of Europe. And then I said, convert it into a stars object, which has essentially an empty attribute, has an attribute in 0 values. And then it's a 30 by 20 grid with 1 degree grid cells associated to WGS84, covering a large part of Europe. And then I did this, not going to talk about what that means, maybe in the break, and loaded some R natural Earth data, which is global Earth data with some parameters, and downloaded the Europe subsection, which includes Russia, and then computed population densities by basically taking the population estimate and dividing that over the area of each of the polygons. This is polygon data. And then I convert the units to 1 over squared kilometers, yeah, to not get very crazy values, very crazy low values, because the SI is of course 1 per square meter. And then I plot these data, and I'm next going to rasterize that. That means that I'm going to take the population density polygon data and rasterize this over this object X that I just made, which is the 1 by 1 degree grid, and it just sort of does the rasterization and takes the population density values for these grid cells, right? And I do that here. So it's a very coarse map of longitude, latitude. You see that although the grid cells are square in terms of degrees, yeah, you think square grid cells, 1 degree north and 1 degree east. Of course, 1 degree north and 1 degree east doesn't everywhere on the world mean the same distance. Yeah, so you see now that the plot methods, given geographical coordinates, take an aspect ratio so that in the middle of the map, roughly 1 meter north equals 1 meter east, which is not the case for degrees, right? So it does an aspect ratio correction on what is essentially an equidistant rectilinear projection. Yeah? So it plots degrees, latitude, longitude as if it was X and Y, but an aspect ratio correction to make sure that countries have the kind of the shape that you're familiar to, and they're not like Germany is this compressed Germany, this kind of round Germany, which you see when people ignore that. Right? So this is something you do, and if you do that, then you also see that the raster is has no longer square grid cells, yeah, but has grid cells that in kilometers in the center of the map roughly has 1 degree and 1 degree. And you see that 1 degree latitude is like 0.8 degrees longitude. That should be the other way around. Okay. So what it can do, what I wanted to make the point now is if I'm going to transform this to another coordinate reference, for instance, the ETRS 89 Lambert equal area projection, which is the recommended European sort of plotting, which is at least equal area plots of Europe, then I can do this for this grid, for these grid values, and I get something that is that now looks the same, it's the same data, and is still a 30 by 20 grid, but has a different reference system and has a big bunch of coordinate values. And it says, I'm a curvilinear grid, right? So what I essentially did here was nothing but just change the coordinates of every grid cell. So although here I knew the coordinates because I could compute them from my regular discretization, now I'm moving them to a new system, which is iterative, where I have to compute for every grid cell, I have to compute the coordinates in the new coordinate system, and they look like this. Yeah, so it's still a regular 20 by 30 grid, but every grid cell now has its coordinates in this coordinate reference system, which is EPSG 30 35, which is the ETRS 89 LEA a projection that actually every European citizen should be aware of, that this is the way to plot your European, to use for your European maps. It should look familiar, right? All European publications will use this, yeah, I think. Right, so it's still a grid. It's just not, it's no longer regular. It's no longer regular. It's so-called curvilinear grid. And that can be convenient or inconvenient. Convenient thing is that all the grid values are still there. I didn't change a single grid value. I just changed the geometry. Yeah, the geometrical transformation. And of course, at some stage, you want to work then with other systems that need regular grids and so on. Then what you can then do is warp this grid. And warping means that I have some kind of odd-shaped thing, and I'm going to burn it into a new regular grid. Yeah? Or you can warp from anything to anything. But this is what's happening here. I take this curvilinear grid. I'm going to make a target grid. The target grid is just the sort of the default grid sizes that takes the bounding box of my population data on this reference system. And then what happens is that it's going to redo the values. Yeah. So here you see then the plot of that new grid. Then you see here the sides. You see the raster cells are much, much, much smaller. And of course, in the values, you still see this blocky thing of what I had here. It's just rasterized to a new raster, which is a regular raster in ETRS 89 LAEA. Yes.
If you open a chat, there's a question about some missing data set in the external test. If you open the chat.
I don't know how to open the chat.
Just go to your Zoom. Click on the Zoom button. You don't have to stop sharing. Okay. Maybe you have to stop sharing. Stop sharing the screen.
Yeah, then I get back to my thing.
Now you go to chat and use a question.
Can I load it? Yes, you can load the Muse dataset. That's a good question. So if you don't have this dataset, you may have to install the raster package. Yeah, because that is where it's going to read this from. This data from. If you install the raster package, you will not have no problems to do this. Okay, good question. So this is what warping does. Yeah, so it warps one sort of raster in one coordinate reference system to a raster in another coordinate reference system. And it means it's going to recompute values. Yeah, so the totals of your raster will no longer be the totals. So for density, this still makes some sense for population density. If I had done this for population numbers, it would have been entirely senseless, right? Because I would have to redistribute population here over raster cells, and then re-rasterizing that will sort of destroy the whole idea because they are kind of extensive variables. So in that case, you would use interpolate area weighted, use area weighted interpolation to go from one rasterization to another one, and do that on a polygon basis. Yeah, the way Carter would do it. Good. So now so are there any questions related to the multi-layer rasters, curvilinear grids, grid warping, RGBing? Then we will go to the more exciting things, which is raster data cubes, time and multiple attributes. So we haven't seen any time variability here. Now we're going to load a data set that is a small data set that's available in the package stars. That's a NetCDF data set, right? NetCDF is a format that has been around. I think it was one of the first sort of libraries that I discovered online. This is in the decades before HTTP was invented. It's in the time that we used FTP to sort of discover data sets, right? You would FTP to some. First of all, you would go to groups, to Usenet groups, and see what's there, right? So read emails and sort of mailing lists distribution system, and see where you could find things. And there would be NOAA sites or something like that, and they would have NetCDF files and a library called NetCDF where you could read and write these things, right? This thing still exists and has sort of developed over the years and is still dominantly used by modeling communities, right? So they use it for spatial temporal data, usually gridded data. And for data where you have multidimensional grids, typically time varying things like weather data, like Earth observation data. A lot of things are NetCDF data sets. So here this thing is being read, and you can see that it reads two sub-data sets or two sort of attributes in this data set, and it has a three-dimensional grid layout where we have an X and a Y. And you see that the deltas are 1/8 of a degree, but you don't see a reference system. Yeah? So it's unclear, this is degrees, latitude, longitude, but it doesn't say so. And then we see that there are two values, precipitation and something with temperature. And you see also that it reads units. Yeah? So these data sets come with actual measurement units, yeah? which is very cool. And they are being read and they're being propagated using the units package, which is another story, which is an extremely good idea, but occasionally causes some headaches for people because sometimes you need to get rid of the units before you can do a next step. Yeah, if you want to plot things with ggplot, that not always works directly. Here we plot this data, and you see what it plots is a sequence of maps that looks over the last dimension. Yeah, so these are 81 by 33 raster data sets, and I have 12 of them. I'm going to plot them, and the labels are the dates that are associated with each of the sets. And these are apparently monthly something, yeah, monthly averages or monthly totals of precipitation, probably total precipitations and average temperature. Yeah, otherwise, it wouldn't make sense. But we would have to look in the metadata of this data set to get more information about who created it, for what purpose, what it is exactly. I think this is climate, downscaled climate data. Another example here is where we have data that are distributed over several NetCDF files. And this is typically by monitoring programs where a satellite flies over and measures something, and somebody analyzes that data and sort of converts it into some kind of product like sea surface temperature and uploads a new file every day, right? Instead of sort of rewriting a very large file that's getting larger and larger, a file is added every day, and you see here that the date is part of the file name, so that makes it easy to find these things. Yes, question?
You have a warning, your battery.
Oh, thank you. Oh, that's a good, yeah. Oh, yeah. Good point. Thanks a lot. It should work. Yeah, it's half an hour to go. Other questions or warnings? So we have a set of NetCDF files here, and it's going to read them in a single bunch, and the read stars here is going to sort out that, oh, this is all sub-data sets that seem to be arranged along a time axis. It's actually going to into each of the files and read the timestamp for it, and then sort of collate it into a regular time dimension, where you see that I have 9 time slices, and that this is the first value. So this is an offset. This is a POSIX CT structure. So you see the POSIX CT value of the first, which is 2 hours Central European Standard Time. So it's midnight UTC. Just my system wants to plot it in my local time zone, which you can change, and has a delta of 1 day. Yeah, so it sorts out that this is regular time. This is a regular time axis, and it doesn't know whether this is associated to time point values or time intervals. That is not in the metadata. Although NetCDFs actually can have that as metadata. It can, if you do temporal aggregations, you can say my temporal value is time bounds. It's really an average or a maximum over a certain time period. So it can do these things. Yeah, and then it is weaker on the spatial thing because it doesn't have a coordinate reference system for whatever reason. Yeah, that's probably encoded in a way that is not interoperable, or that GDAL doesn't recognize. GDAL doesn't recognize as degrees in some kind of associated to some kind of data. What you also see is there's a 4th dimension, which is called Z level. Well, this is sea surface temperature So it's a surface, right? So there's not much interesting going on in the elevation. It is zero, it is sea surface. So this is 0 meter. So it has essentially a unit for the elevation, but it's a single layer elevation. Yeah? So now it has metadata. This is on a certain elevation that I know, 0 meters with respect to sea level, but it doesn't have any variability here because it is surface temperature. And that causes a bit of trouble. Sometimes if we want to plot it, it's going to loop over the third dimension and so show the sea level, which is not terribly interesting. The more interesting is the variability over time. So I can drop this, I can use a drop to drop singular dimensions, yeah, dimensions that have only one value. Yeah, so it's a 1440 by 720 by 1 by 9 array, but if I drop that one dimension that has only one value, it remains the same information. I just lose the information that this is at 0 level. Yeah? So I have to, so it's there, it's in the data, it's a 4-dimensional array, but with an, so to speak, an obsolete third dimension. So a drop drops that one and retains the other 3 that have variability, and then I could plot it. And here is an example where I used ggplot and gmstars with a couple of other things to plot these data and the Viritus thing and so on. So basically you give it z, and then z1 means the first attribute. If I don't do that, it takes the first attribute anyway. I have a certain alpha value, and I'm going to downsample this. Yeah, I'm going to downsample. That means that although I have quarter degree grid, I'm going to downsample this to a 2.5 degree grid, because my plot is anyway so small that every single pixel is probably already 5 degrees or something like that. So I don't have to do that, but I'm doing that because otherwise it takes an eternity before this plot is finished. Otherwise it's going to do all the pixels. Yeah, and then it takes like 5 minutes, and every time I compile my slides, I have to wait 5 minutes. I don't know if it's 5 minutes, but it's a factor 100 that I'm reducing here, the number of pixels that I show. And in the end, the thing looks the same, pretty much. The downsampling is something that we haven't seen before, but it also happens here. It happens in every plot command, but these are base plot commands. And there I can, you know, when I do a base plot, can check what is my device, how many pixels do I have, how many pixels does my array have. Here I'm in ggplot, and you can no longer do this because you are sort of lost in the ggplot abstractions of everything, right? So at the moment that ggplot, you know, ggplot distributes tasks, at the moment that you're in a geom_something, you cannot sort of ask ggplot, how many pixels does my device actually have? You cannot do that. Yeah, interestingly, I had discussions with some of the real sort of ggplot gurus, Thomas and Klaus Wilke, Thomas Pedersen, and so on. And no, you can't do this. You can't do this, which is very regrettable. Yeah, that we can't do this. Yeah, so sometimes ggplots will take eternity to finish. Yes, and then remember that you can do this downsampling by hand, regrettably, which you could do automatically if you knew. If it, you know, that worked. Anyway, yeah. So this is developer talk. But also warnings that some things, you know, are difficult to do in R. Other operations on data cubes are subsetting. We already saw. If I take the first sort of a single index, then what happens is I just do a list index. Stars objects are lists with a class and a dimension table in an attribute. They are lists of arrays. So if I do a selection of the first element, I just get the first list element, the second list element, which is here the anomaly, which drops all the other arrays and keeps the dimension table because that doesn't change. Other things is that I can select other elements by saying comma. Comma means that I select all the first attributes, right? If I don't specify anything, I select everything. So it selects attributes, it's the first square bracket selector. Then it selects the first dimension, second dimension, and so on. So first and second dimension are X and Y. So now I selected a subset that has the first 10 rows and the first 12 columns. It's reversed. The first 10 values of the x variable, meaning the first 10 columns, and then the first 12 of the second dimension was the first 12 rows. It's columns, rows. This is how the thing is organized. There is this fortune about illogical, which is one from Brian Ripley in 2004. Mathematical conventions are just that, conventions. They differ by field of mathematics. Don't ask us why matrix rows are numbered down, but graphs are numbered up the y-axis. Nor yx comes before y, but row before column. Right? This is what I just mixed up. Yeah, and you always say row column, and you say x y, but x is column and y is row. Right? So if you talk, it's just conventions. Right, the sea level is still in there, and I retain my rows and so on. And you can also select on sea level. Of course, I only have one there, and I can also select on time. Yeah, it means that I need 4 commas, right, for the attributes x, y, and z level, and then I get a smaller time slice, right? I select from time item 5, 3, from 3 to 5. Yeah, and you see here that now you see why the from is there, because I selected from 3 to 5, but I still have the same offset. Yes, and if I would say, okay, those are 3 time instances, I do from 1 to 3, then I need to recompute the offset, yeah, because the offset shifts. Yeah, so that is why this from field, and this is sometimes confusing. There is an st_normalize that undoes that. Yeah, that will sort of change this into from 1 to 3 and then modify the offset value with the appropriate number of deltas. Right. Subsetting can also be used to shortcut intersections, as like here, if I do a global grid and then I plot sort of the section that intersects with the European polygons. Let me see if we can do that. I think I didn't do that because it looks very ugly, and it looks very ugly because NE is a European data set that includes entire Russia and that crosses the date line. So you end up with a grid anyway that is global because the date line is involved and all that kind of ratio. So I didn't actually do this. But the idea is there, right? So you do an intersection, you select by sort of the area, you basically crop the area by a certain geographic region that can be a simple feature geometry. Other things you can do is cropping, or making sort of a sub raster with smaller area, or you crop by a polygon set, and you then basically burn in NA values in all the cells that are outside this area. There's a couple of tidyverbs, tidyverse type verbs that work with stars object. There is a slice that selects dimension values using the index. There is filter that selects dimension value using the dimension value. So you filter, you use coordinates. For slice, you use index, you use rows and columns. There is pulse that pulls out an attribute. Select that selects attributes, and mutate that computes new attributes based on existing ones. Yeah, so you could mutate and then say compute SST times 5 or something like that, or some conversion into Kelvin or some conversion into Fahrenheit or something like that. Do that on an array-based basis, right, for all of the cells. Then there are also these kind of map algebra type things where you can I'm now loading the data set from the Landsat imagery, and it can, for instance, multiply by 2, and it gets something didn't go to 255, it goes to 510. And it can also do things like mask things out. So for every cell that is smaller than 125, give that a value NA or something like that, and then basically do these kind of array logic, right? So you basically retain all the cells that have values larger than 125. Yeah, so a number of sort of things that you could do that you think map algebra like expressions you could actually do with these stars objects. There is the things like from raster to vector, from vector to raster, which is one of the things that you quite often wanted to do. We already saw the STSSF, which basically takes rasters and then draws either points on all the raster cell centers or draws little square polygons around all the rasters, depending what you want. That is one way. There is the rasterize that we saw that goes from vector to raster and rasterizes then. That essentially calls the GDAL utility. It's part of a GDAL library, the rasterize routines there. And then there's the issue of proxy objects. Yeah, so there's a couple of ways of going from raster to vector and vice versa. There is extract, which samples at point locations, and there's aggregate that aggregates cells over polygons and computes whatever function, the sum or the mean, over that polygon of all the values. There's even a very fancy one that does that using the package exact extractor, which is a terribly fast and good package for computing aggregates over polygons that basically cuts little square raster cells into parts and sort of use the weights of the part of the raster cell that falls into the polygon part that falls out, so that you get this really area weighted aggregations for sums and means, and that does this in an incredibly fast way with a very clever algorithm. Exact extractor. Exact extractor by Daniel Beston, one of the SF contributors and GEOS developers. Then there's the thing, how do I work with large raster data? Yeah, so I have my hard drive is full with Sentinel tiles and so on. I'm going to go through that. The package raster does that in a particular way that is not too transparent. We do that in stars. We also do that in a somewhat different way, in the sense that we have this idea of proxy objects, and I'm doing that here with a Sentinel-2 granule or tile or scene or whatever you want to call it, that is available in the stars data package. So I'm going to create here this file name, which is a very long file name, which has a prefix essentially to tell GDAL this is a Sentinel-2 L1C dataset, and tell where it is, and then give sort of the long thing of the thing that it needs to read inside that zip file to get the metadata, and then it reads it. Yeah, so this is all this is all something you need to do once, and then for every Sentinel-2 tile it works the same thing. So it's going to read it here, and what you see is that what I get back is the star's proxy object with one attribute in this file, and this has the 4 10-meter bands. Yeah, you see here that bands are named B4, B5, B6, and B8, I think, and that I have 11,000 by 11,000 pixels, each of 10 meters size, and they're in a particular UTM zone associated. Yeah, so this is the 4 10-meter bands in a Sentinel-2 tile, and it's not reading anything. So this takes like less than a second because it doesn't read anything. It just says the data are here. I know where the data are, and this is the metadata, the dimensions. Yeah, so it tells me sort of the dimension of this array without reading it, because reading it would sort of take a lot of would take most of your memory probably. We can control whether this is being read as a star's proxy by setting proxy as true, but at the current state of affairs, it's being read as a proxy object by default because it's so large. So it's first going to read the dimension of the thing and then decides, okay, there are more than 10 to the power 8 cells. I'm not going to read this into memory because most likely you don't want that. I'm going to have this as a proxy object, and then it tries to do lazy evaluation. That means that it doesn't do anything up to the moment that you wanted to do something, right? So at some stage you want to do so you can compute, for instance, here NDVIs by applying a function called NDVI that computes here NDVI values over the band dimension to the x and to loop that over the x and y dimensions, right? So apply it to the bands. Yeah, this is the expression. So band 4 is near and band 1 is red. So if you do this, it's done within within a microsecond, because still it doesn't do anything because you didn't ask for pixels. It just says, okay, I still have this property object. It just now has a call list. I need to do something. So if you want to have something, I'm going to do something. Now, if you plot this thing, it also does that in like something like seconds or so, because what it does is basically it computes as many pixels as you have. It computes as many cells as if you have pixels on your screen or on your device. Right? So you can do this on a 10-meter resolution, compute the NDVIs, and it would take like 10 minutes to read the whole thing and then compute it and probably write it back because it's too large to hold in memory and so on. So it would take 10 minutes. But if you only want to plot this, then you basically look at a plot of, what will it be, 600 by 600 pixels or something like that. And I'm now going to loop over these 600 by 600 pixels, read them, compute NDVIs, and plot them. Right? So this is a bit of a trick. So this plot.ndvi actually looks at this object and say, okay, there isn't this object, but it still has homework to do, but I need to plot. So let's look at what the homework does. Oh, it's an ST apply. Oh, it doesn't do anything spatial. It only works on the bands. So I can do it for just as many pixels as I need. There's no filtering going on. If there was filtering, I, of course, couldn't do this trick. Yeah, so it looks and says, okay, I have to do something. And do this at the screen resolution and then plot it, and that speeds up things from, as I said, from something like 10 minutes when you would do it for the entire data set to something that is within seconds done. And the trick it does, of course, is that it uses image pyramids. It uses the overviews. This raster tile comes with lower resolution overviews of all of the bands, and if you're asking sort of a downsampling of whatever a factor 600, then it can work on one of these overviews and only read a very small amount of the actual data set. Now, this is a pattern that everyone who worked with Google Earth Engine is familiar with. Basically, what that does is that it just computes your screen pixels, yeah, and then you zoom in, it's going to recompute the screen pixels. So although you work on massive imagery, you just do computation that are sort of proportional to the plot size you want to have. Finally, a more complex, a more real example that I sort of cooked up in the last few days, because I discovered that Marius Appel's material for tomorrow was online. So I'm always curious, like, oh, what's going on there? So Marius will do a sort of a serious, sort of quasi-serious scaled data cubing, yeah, because it's not going to work with petabytes, because you don't have petabytes on your laptop, but it's going to work with data sets the size that you can still download it and work on it locally to get the idea. And Marius compiled a number of Landsat 8 scenes for a particular area, over a particular time range, and creates cubes from that. And I was going to give a very poor man's version of that. Yeah. So what I do, for instance, is I look at only at a single scene, so I don't have to worry about all different places and times and so on. They're typically satellite image scenes. They're not in a cube, right? So it's an orbiting satellite. So it's a trajectory of images you get. The STARS has an ST mosaic, so you can mosaic things together, but you then need to first sort out which things to mosaic. Yeah, and that is exactly what GDAL Cubes does. What I sort of did not do here, but I downloaded Marius's data set, which is here. You can you saw all these tiles here, which are in directories, and in one of these directories you see a number of TIFF files. I'm going to and we're going to load the 7 bands of these geotiffs and do this in this particular scene. So I'm going to match all the file names that match to this pattern, so band 1 to 7, from essentially from this, the directory that starts with this expression. And then I'm going to read all this, so that gives me like 120 files. I'm going to read all of them in memory, so not as proxies in memory. And then I'm going to warp them. I had to do that because there was tiny differences in there. I couldn't sort of put them on, as a pile on top of each other. There was like slight differences in the number of rows and columns, so I'm going to warp them anyway to the geometry of the first one, right? Hopefully not too much gets lost. And then I'm going to glue them together, which can be done by the C. Basically, I do a C with the 120 objects, combine them, and then I get essentially that set. And then I got the time series actually from the scenes somehow, right? Because the time, yes, you can see here, the time is encoded in the scene name. So that's going to happen here. I'm extracting this little section of the file name, and I'm going to read that with this format string, and I get my times. Yeah, it's a very sort of obscure way of doing that. I wouldn't recommend it to anyone, but it's possible with R. Then I'm going to take the band name from the file name that takes this little string, right? That tells me the band name. So I get band 1 to 7 and so on. And I'm going to merge this whole thing. And then I see that I have a 760 by 770 raster with 182 layers. And then I have to assign band and time, because these 182 layers are 7 bands for like something like 40 different time instances or so like that. So I need to then redimension this thing. And what I sort of do, and now comes the ugly part. So this is why, why you need proper packages that do this in a sort of in a readable way. I'm going to sort of just work on this raw dimension table, remove this attribute, and then create 2 new dimensions. Actually, one with the unique dates and one with the unique bands. And I'm going to redimension this thing. And then you see the dimension table looks like this. So I have now 26 dates, yeah, which have all date, and which apparently have no offset and delta, so they're not regular. They're not found to be regularly distributed in time. And they have 7 different bands. And the question is whether everything is correct now. And I'm not entirely sure whether everything is correct. I just did this. Yeah? So I hope everything is correct. Yeah? Spatially, it will be okay, I think. Just the assigning of dates and bands, I'm not sure, because it looks odd. This might look okay. So here I do a slice over date. So I take one particular date. So the first date, which will be the 6th of August. And then you get a plot of the 7 different bands for that date. So this is a time slice. This was the essential hint, thanks by that all values smaller than 0 were missing. So I had to assign them NA. You can do this for a 4-dimensional array like this. And here I did a plot of a time series of the first band. So this is band 1 and a time series, and I'm entirely unsure whether this makes sense. But anyway, you can get an idea. Time slices, band slices, and look at these data as a data cube and sort of get through them. And you can even compute NDVIs by doing the same trick, but then with band 5 and 4, which apparently correspond to near infrared and red, and apply this to the first 3 dimensions, X, Y, and time. So we compute NDVI we use NDVI function to reuse the band dimension, and we get back a 3-dimensional data cube that is now just a time series where band was reduced to NDVI, and we get these NDVI time series. I'm not sure whether they really make sense, but this is what came out. So it's still kind of work in progress, but just to show how you can manipulate these sort of, this is all in memory, but in principle you could do all of these kind of things out of memory, but and sort of still have plots, exploratory plots, and do simple functions on dimensions in a relatively responsive fashion. So without doing the full computation on the entire high dimension data cube, right? You see very small subplots. So the number of pixels that are being computed is also very limited. It's just kind of the same number of pixels that you see here, maybe 100 by 100, rather than the sort of the 700 by 700. So that is a kind of a factor 50 speed up that you get in the plotting action there. So these were some demonstrations of how you can juggle around with vector data cubes, with raster data cubes, where it really becomes exciting if you have more than 4 dimensions, more than 3 dimensions. So more than 3 dimensions is also the use case where, at least as I understand it, the raster package and its successor, Terra, kind of where you get stuck because it has a raster stack as its multidimensional thing, and if you have a stack of bands and times, then you need to do the whole administration, like where are my times, where are my bands, and kind of you can do a function through that, but it's not, they're 2 dimensions, right? And the data structure you can handle is really 3-dimensional and doesn't sort of work with more dimensions than that. So that was one of the motivations to do this work. So are there any questions from your side, which I can take and then repeat? So nobody in the field will hear it. Yeah?
Terra has, for example, very efficient overlay for like large geotiffs. It works very fast. I mean, you don't have to load the geotiff in memory. Is your stacks also efficient in?
Well, as I said, if you have a complex data cube object like here, like in this last example, when I do this plot, so if I use star's proxy object, so here at this moment everything will be computed because the thing is in memory, right? The whole thing fits in memory, it is in memory. But if it's a star's proxy object, then it has this lazy evaluation. So the object is on disk, might be massive, but it looks at the order of operations and says, okay, you want to plot? Plots, how large is my plotting device? How many submaps am I going to plot? How many pixels do I need for a single subplot? Oh, that's 100 by 100. So I'm going to subsample and just read at a lower resolution. Yeah? And that goes to GDAL, and GDAL is very fast in doing lower resolution operations. But you don't have to tell it that. It does this because it knows it's a plot. I only need so many pixels. I know, does Terra the same thing? Does Terra the same thing?
No, I don't know.
I also don't know. There's very little information about what Terra actually does and what it doesn't do.
So we use the Terra for the overlay, so it's the most efficient.
I don't know what overlay means.
But the extract, I mean, Terra
Extract. Yeah.
So it's very efficient. It's a C++.
Well, you know, it's a lot of things here are also done in GDAL, which is C++, and that's what Terra also does. It also calls C++, calls GDAL routines. I hope it does, because we understand what they do. But it also does a lot of things in ways that are sort of hard to track down the exact details. So yeah, well, this is not, I mean, this is unfriendly to say I'm very sort of, I'm a big admirer of Robert Hammond's works. We looked at RGB composites of plots, and I looked at what the MapView code did to do this, and I looked at some other package that also did that, and they all would sort of look at RGB values and then take this 2 and the 98 quantile and throw everything outside of that away, basically set it to the 2 and the 89 quantile, and then use that range to compute RGB values to do a stretching. And that happens to come out of raster code, which is not documented, where you can't control the quantiles, but it does that, and it doesn't show up in the help page of the plot RGB command. So plot RGB does that, and if you want to reproduce what plot RGB does, you can look in the code, and you see that it does that. But it doesn't explain that it does that, and it doesn't explain why it does that. So these are the kind of the little things that kind of start to live their own life, and then people copy that because they think plot RGB is the thing that is true, right? Because that was there first and everyone uses that. But I don't know why you picked the 2nd and 98th quantile and not the 5 and 95 or the 1 and the 99 or the whole range. Yeah, there are always like funny values at the tails in a lot of satellite imagery, funny high values. So if you take the data range as a default, which might also make sense, then you get completely black images, right? These kind of things. So there is stuff that you ran into, which is kind of came up for that. Probably Robert got his inspiration from somebody else, but we don't know, and it's not documented. At least I couldn't find it. Are there other questions? Yes.
Provide more or less all functionality of the raster package, or are there some functionalities that are not covered?
I don't know what all the functionality of the raster package is.
I don't know, extracting maybe and aggregating.
Those are the 2 common use cases. That is what it does. Yes. Yeah.
Can you do image filtering?
But so if you look at sort of if you look at the amount of functions that the raster package provides, it's massive. I don't know. Multi-core things. I think the I think that ST-apply has a couple of options, because apply is always like independent job, because you work on dimensions. The chunks are always independent. So ST-apply has options where you can pass a cluster and tell whether to use future or to use some other parallel apply or something like that. ST-apply has parallelization options.
Open functions, so like a moving window.
Right now, it doesn't do that. No, there is an issue on GitHub where somebody asked that, and I did that by converting it to a raster object, calling focal on the raster object, and converting back. So that was like a 3-liner or so that you could throw in ST-apply, because the focal is essentially over X and Y dimension. You leave everything else intact. Yeah, so for each of the time, for each of the bands, you do the focal on the XY slice. Yeah. So if you could, I think I'm offline because I did some VPN stuff that I shouldn't have done. No, I'm not. So if I look at stars issues and then search for focal filter with stars. Here's an example. So you do an ST-apply with the focal function. Yeah, that doesn't cause focal and raster. So does the raster conversion on the fly and calls focal there? No. Yeah, we could port this code. This is also kind of the same thing. The question is how this will work with massive grids, but I don't know how many people want to do focal things on massive grids. I think you can do star proxy things with raster as well. I have to look at it, because it's essentially raster does the same thing, right? So it says, here's the file name, and then I'm going to work with that and sort of return when I'm done. So yeah, that is relatively, they work to, sort of stars provides the from raster and to raster conversions, and you can call things there if it's convenient. In any case, you don't have to sort of work out your band and time things then. Yeah, and the other thing is the conversion integration with SF, which is pretty natural, because it's kind of, in that sense, stars extends SF for multidimensional feature or feature time series or multidimensional feature data. Are there any other questions? So yeah, so as I said, there is this R Markdown. So I hope that there are some people who actually managed to run the whole thing in the meantime. Yeah, good. Okay. So in the meantime, while I was talking, it's sort of the run all button on RStudio after installing a few sort of bigger packages. When you don't manage, then catch up with me in some break sometime. I'll be here until Thursday morning. And happy to discuss things, or happy to also explore all the things you cannot do with stars, right? So,